So in PN junction diode which has 2 terminals, तर PN junction diode ला काय कोणते 2 टर्मिनल आहेत, एनोड टर्मिनल अँड कॅथोड टर्मिनल. तर आपण थेरी सेशन मध्ये पाहिलेलं PN जंक्शन डायोड चा सर्किट सिम्बॉल, फिजिकल स्ट्रक्चर डायग्राम जी आहे ती आपण सेकंड युनिट मध्ये पाहिली होती. तर PN जंक्शन डायोडला काय आहे की 2 टर्मिनल आहेत, एनोड टर्मिनल अँड कॅथोड टर्मिनल. तर एनोड टर्मिनल जो आहे पॉझिटिव्ह टर्मिनल, कॅथोड टर्मिनल मीन्स व्हॉट, निगेटिव्ह टर्मिनल. तर एनोड मीन्स व्हॉट पॉझिटिव्ह आणि कॅथोड मीन्स व्हॉट निगेटिव्ह. तर सिल्वर कलरची रिंग साइड आहे, तर ती आपण काय करतो, एनोड कॅथोड टर्मिनल जे आहे दॅट वी कन्सिडर. देन सेम सर्किट सिम्बॉल वी हॅव स्टडीड फॉर झिनर डायोड. सो फॉर झिनर डायोड सर्किट सिम्बॉल मध्ये स्लाइटली चेंज आहे, फक्त आउटपुटला काय केलेलं आहे, स्क्रीन शेअर केलेली नाहीये, 2 मिनिटात व्हिडिओ शेअर करते मग. तर याच्यामध्ये की आपण काय करणार आहे, याच्यामध्ये आपण काय करणार आहे, तर झिनर डायोड जो आहे, तर झिनर डायोड चा सर्किट सिम्बॉल जो आहे तो स्टडी केला. तर झिनर डायोडला पण सेम 2 टर्मिनल आहेत, दॅट इज एनोड टर्मिनल, कॅथोड टर्मिनल. एनोड मीन्स व्हॉट पॉझिटिव्ह टर्मिनल, कॅथोड मीन्स व्हॉट निगेटिव्ह टर्मिनल. तर झिनर डायोड जो आहे तो आपण मोस्टली काय रिव्हर्स बायसिंग ऍप्लिकेशन मध्ये आपण काय करतो, तर झिनर डायोड जो आहे तो सर्किट मध्ये यूज करतो. देन याच्यामध्ये आपण काय स्टडी करणार आहे, तर कॅरेक्टरिस्टिक स्टडी करणार आहे PN जंक्शन डायोडच्या. तर फॉरवर्ड कॅरेक्टरिस्टिक अँड रिव्हर्स कॅरेक्टरिस्टिक्स मॅन्युअल मध्ये तुम्हाला दिलेल्या आहेत, फॉरवर्ड कॅरेक्टरिस्टिक्स अँड रिव्हर्स कॅरेक्टरिस्टिक्स. तर फॉरवर्ड कॅरेक्टरिस्टिक मध्ये काय करतो की फर्स्ट क्वाड्रंट मध्ये आपण काय करतो, तर फॉरवर्ड कॅरेक्टरिस्टिक जे आहे त्या प्लॉट करतो. थर्ड क्वाड्रंट मध्ये आपण काय करतो, रिव्हर्स कॅरेक्टरिस्टिक्स जे आहे त्या प्लॉट करतो. तर फर्स्ट क्वाड्रंट मध्ये की इनपुट व्होल्टेज ज्यावेळी व्हॅरी करणारे दॅट टाइम आउटपुट करंट जो आहे मिली अँपियर मध्ये आपण काय करतो, मेजर करतो. तर फॉरवर्ड कॅरेक्टरिस्टिक मध्ये आपण पॉइंट जो आहे कट इन व्होल्टेज मेजर करतो. सो कट इन व्होल्टेज मीन्स व्हॉट, की व्होल्टेज ऍट विच करंट स्टार्ट्स इन्क्रीजिंग, दॅट इज कॉल्ड ॲज अ कट इन व्होल्टेज. तर कट इन व्होल्टेज जे आहे दॅट इज इम्पॉर्टंट पॉइंट. So cut in voltage means what, the voltage at which current starts increasing, that is called as a cut in voltage. Then रिव्हर्स कॅरेक्टरिस्टिक मध्ये आपण काय करणार आहे, ब्रेकडाऊन व्होल्टेज जे आहे ब्रेकडाऊन व्होल्टेज मेजर करणार आहे. तर ब्रेकडाऊन व्होल्टेज मीन्स व्हॉट, मॅक्सिमम व्होल्टेज अक्रॉस द डायोड इन रिव्हर्स बायसिंग मोड, दॅट इज कॉल्ड ॲज अ ब्रेकडाऊन व्होल्टेज. तर आपण काय करणार आहे, ब्रेकडाऊन व्होल्टेज जे आहे ते सर्किट मधलं मेजर करणार आहे. देन PN जंक्शन डायोड मध्ये तुम्हाला फॉरवर्ड बायसिंग आणि रिव्हर्स बायसिंग कन्सेप्ट जो आहे तो मी एक्सप्लेन केला होता सर्किट डायग्राम वरून. तर फॉरवर्ड बायसिंग मध्ये काय होतं सांगा, चॅट बॉक्स मध्ये शेअर करा. फॉरवर्ड बायसिंग मध्ये काय होतं की ज्यावेळी आपण इनपुट व्होल्टेज सोर्स अप्लाय करणार आहे, मीन्स एनोडला पॉझिटिव्ह व्होल्टेज, कॅथोडला निगेटिव्ह व्होल्टेज, दॅट टाइम तुमच्या डिप्लेशन रिजन मध्ये काय असणार आहे, इलेक्ट्रॉन्स आणि होल्स असणार आहे. सो in depletion region, that is positive ions move towards the positive direction of voltage source, negative ions move towards the negative terminal of the source. That time what will be the effect on depletion region. तर फॉरवर्ड बायसिंग मध्ये काय होतं, डिप्लेशन रिजन ची विड्थ काय होते, चॅट बॉक्स मध्ये शेअर करा. फॉरवर्ड बायसिंग मध्ये PN जंक्शन डायोड असेल किंवा झिनर डायोड असेल, तर फॉरवर्ड बायसिंग मोड मध्ये काय होणार आहे, डिप्लेशन रिजनची विड्थ काय होणार आहे, फॉरवर्ड बायसिंग मध्ये डिप्लेशन रिजनची विड्थ काय होते, इन्क्रीज होते का डिक्रीज होते. तर फॉरवर्ड बायसिंग मध्ये काय होतं, इलेक्ट्रॉन्स आणि होल्सचं रिकॉम्बिनेशन होतं. रिकॉम्बिनेशन मीन्स व्हॉट, सर्किट डायग्राम ज्या आहे त्या ड्रॉ करून प्रॅक्टिस करून बघायच्या. काय होतं सांगा, फॉरवर्ड बायसिंग मध्ये डिप्लेशन रिजनची विड्थ काय होते, इन्क्रीज होते का डिक्रीज होते. MCQ बेस्ड एक्झाम मध्ये पण तुम्हाला क्वेश्चन जो आहे तो विचारला जातो. फॉरवर्ड बायसिंग मोड मध्ये डिप्लेशन रिजनची विड्थ इन्क्रीज होणार का डिक्रीज होणार? तर फॉरवर्ड बायसिंग मोड मध्ये काय होतं, डिप्लेशन रिजनची विड्थ जी आहे ती डिक्रीज होते आणि रिव्हर्स बायसिंग मोड मध्ये काय होतं, डिप्लेशन रिजनची विड्थ जी आहे ती इन्क्रीज होते. तर डायग्राम ड्रॉ करून वर्किंग जे आहे ते पीएन जंक्शन डायोड झिनर डायोडचं दोन्हीचं कम्पेअर करून बघा, म्हणजे लक्षात येईल. तर फॉरवर्ड बायसिंग मध्ये डिप्लेशन रिजनची विड्थ जी आहे डिक्रीज होते आणि रिव्हर्स बायसिंग मोड मध्ये डिप्लेशन रिजनची विड्थ काय होते, इन्क्रीज होते. आता सेम मी काय करते की तुम्हाला हा जो व्हिडिओ शेअर करणार आहे, या व्हिडिओ मध्ये तुम्हाला डिप्लेशन रिजनची विड्थ इन्क्रीज डिक्रीज कशी होणार आहे, तर इलेक्ट्रॉन्स आणि होल्स जे आहे की ज्यावेळी आपण सप्लाय व्होल्टेज पास करणार आहे दॅट टाइम सर्किट मध्ये इलेक्ट्रॉन्स आणि होल्सचं रिकॉम्बिनेशन होऊन त्याचा इफेक्ट डिप्लेशन रिजन वरती कसा होतोय तो आपण ऑब्झर्व करणार आहे. तर इथं मी तुम्हाला व्हिडिओ शेअर करते सेम पीएन जंक्शन डायोडचा. सेम प्रॅक्टिकल आपल्याला लॅब मध्ये परफॉर्म करायला आहे. तर लॅब मध्ये आता ऑनलाईन असल्यामुळे फक्त तुम्हाला व्हिडिओ जे आहे प्रॅक्टिकलचे शेअर केले जातील. तर व्हिडिओ मध्ये बघा, दाखवते.
The apparatus used in this experiment are a PN junction characteristic apparatus and connecting wires.
स्क्रीन दिसतेय ना सगळ्यांना?
हो.
व्हिडिओ दिसतोय ना सगळ्यांना?
A P-type semiconductor is the one which has free hole
व्हिडिओ
and
बघा.
impure immobile negative ions. So we can say that P-type semiconductor have excess number of holes and they are majority charge carriers. Whereas N-type semiconductor is the one which has free electron and impure immobile positive ions. So we can say that N-type semiconductor have excess number of electrons and they are the majority charge carriers. The combination of P-type and N-type semiconductors result in a PN junction diode. Here, at the junction, diffusion takes place. Similarly, due to the higher concentration of electrons in the N section, electrons diffuse from N side to P side, leaving behind an ionized positive charge which is immovable. As the holes and electrons continue to diffuse, a layer of negative charge on the P side of the junction and a layer of positive charge on the N side of the junction is developed. This junction region is known as depletion layer. Since either side of the junction region stationary positive and negative charges exist, there is an electric potential difference Vd across the junction which is called potential barrier. It prevents the further movement of holes and electrons. And this whole combination is nothing but the PN junction diode. Here, the white line on one end indicates that it is a negative terminal. Now, let us study the forward bias characteristics. When P section is connected to the positive terminal and N section is connected to the negative terminal of the battery, the PN junction is said to be in the forward bias. With the increase in forward bias voltage, the forward current increases slowly. When the forward bias voltage V equal to the threshold voltage, the forward current increases rapidly. Now, let us move on to the reverse bias characteristics. When the P section is connected to the negative terminal and the N section is connected to the positive terminal of the battery, the PN junction is said to be in the reverse bias. With the increase in the reverse bias voltage, a very small reverse current flows which remains almost constant. When the reverse bias voltage V equal the reverse breakdown voltage, the reverse current suddenly increases to a large value.
Now that you have understood the working of a PN junction diode and the procedure for this experiment, let's make the connections. This is the on-off switch for the power supply for this circuit. When you are making the connections in forward bias, you must flip both these toggle switches towards FB, that is forward bias. When you are making the connections for reverse bias, you must flip both these toggle switches towards RB, that is reverse bias. We will use these two terminals to connect the diode in forward bias and these two terminals to connect the diode in reverse bias. Now let's make the connections for forward bias. As you can see in the circuit diagram for forward bias, the positive terminal of the voltmeter is already connected to the high potential point and the negative terminal of the voltmeter is also already connected to the low potential point. So, to connect the positive terminal of the diode to high potential, we will first connect the positive terminal of the voltmeter to the positive terminal of the ammeter, and then we will connect the negative terminal of the ammeter to the positive terminal of the diode. Next, to connect the negative terminal of the diode to low potential, we will connect the negative terminal of the voltmeter to the negative terminal of the diode. Thus, the diode is now in forward bias since the positive terminal of the diode is connected to the high potential point and the negative terminal of the diode is connected to the low potential point. The voltmeter measures the forward bias voltage and the ammeter measures the forward current in milliamperes. Thus, the connections in forward bias are complete. So now let's start the experiment. Remove the zero errors, if any, in the ammeter and voltmeter. As you can see, the ammeter here has a zero error of 2 divisions while the voltmeter does not have any zero error. So let's first remove the zero error in the ammeter by using the screwdriver. Now the zero error has been removed from the ammeter. Next, we will note down the range and least count of the ammeter and voltmeter. Forward bias, the range of the ammeter is 15 milliamperes and its least count is 0.3 milliamperes because 10 divisions make up 3 milliamperes. Forward bias, the range of the voltmeter is 1 volts and its least count is 0.02 volts since 10 divisions make up 0.2 volts. Let's switch on the power supply. Ensure that both the toggle switches are in forward bias mode. And now let's increase the forward voltage by turning the forward bias knob slowly. Find that while the forward voltage has increased up to 0.3 volts, the forward current is still remaining 0. Let's increase the forward voltage a little more. Find that when the forward voltage reaches around 0.4 volts, the forward current starts to rise. Thereafter, as I increase the forward voltage, the forward current also increases steadily. Let's check till what value of forward voltage the forward current reaches its maximum value in the scale. We find that we will be able to take measurements up to around 0.6 volts so that we can cover the entire range of the ammeter. So let's take our first reading. We'll set the forward voltage to 0.02 volts and we find that the forward current is 0 milliamperes. Like this, we can increase the forward voltage by turning this forward bias knob slowly and take as many readings as possible to cover the entire range of the ammeter and voltmeter. Remember to note down all the readings in the observation table. Now Now that we have taken the readings for forward bias, let's make the connections for reverse bias. First, flip the toggle switches to reverse bias mode. Now, as you can see in the circuit diagram for reverse bias, the positive terminal of the voltmeter is already connected to the high potential point and the negative terminal of the voltmeter is already connected to the low potential point. So, we connect the negative terminal of the diode to high potential point by first connecting the positive terminal of the voltmeter, the positive terminal of the ammeter, and then connecting the negative terminal of the ammeter to the negative terminal of the diode. Next, we connect the positive terminal of the diode to low potential point by connecting it to the negative terminal of the voltmeter. Thus, the diode is now in reverse bias since its negative terminal is connected to high potential point and its positive terminal is connected to the low potential point. This voltmeter measures the reverse bias voltage and this ammeter measures the reverse current in microamperes. This completes the connections for reverse bias. Now, let's perform the experiment for reverse bias. There is no zero error in the ammeter and voltmeter. Note down their range and least. Range of the ammeter is 0 to 100 microamperes. Since 10 divisions make up 20 microamperes. Range of the voltmeter is 0 to 100 volts. 2 volts. Divisions make up 20 volts. Let's switch on the power supply and increase the reverse bias voltage by slowly turning this reverse bias knob. As the reverse bias voltage is increasing, observe that the reverse current is also increasing steadily. Since we want to utilize the full range of the ammeter scale, let's find out at what value of reverse bias voltage the ammeter reaches its maximum deflection. We find that at around 50 volts in the reverse bias, the ammeter reaches its maximum deflection. We will plan our measurements in such a way that we take as many readings as possible till the voltmeter reaches 50 volts. Let's take our first measurement for the voltmeter reading of 4 volts. Now the voltmeter is showing 4 volts. And the corresponding reading in the ammeter is 2 microamperes. So note this down in the observation table and take the remaining readings by increasing the reverse bias voltage slowly by rotating this reverse bias knob. Tabulate all your readings in the observation table.
PN junction diode, forward bias. Range of the voltmeter is equal to 0 to 1 volts. Least count of the voltmeter is equal to 0.02 volts. Zero error of the voltmeter is equal to nil. Range of milliammeter is equal to 0 to 15 milliamperes. Least count of milliammeter is equal to 0.3 milliamperes. Zero error of the milliammeter is equal to nil. Observation table for forward bias voltage and forward current. When the input voltage Vf is increased in steps of 0.02 volts from 0 to 0.2, the forward current If is 0. After that, when the input voltage is increased in steps of 0.1 volt, the input current slowly increases. Using the values of forward voltage and forward current, we plot a graph by taking forward voltage on x-axis and forward current on y-axis. We consider a suitable scale. On x-axis, 1 centimeter is equal to 0.1 volt. On y-axis, 1 centimeter is equal to 5 milliamperes. Origin 0, 0. Now, let us plot the points on the graph. The graph comes out to be as shown here. In forward bias, junction resistance is R is equal to delta Vf by delta If, which is 0.7 minus 0.6 by 15 minus 5. That is equal to 0.1 volt divided by 10 milliamperes is equal to 10 ohms. Junction resistance for forward bias is 10 ohms. Reverse bias. Range of the voltmeter is equal to 0 to 100 volts. Least count of the voltmeter is equal to 2 volts. Zero error of the voltmeter is equal to nil. Range of the microammeter is equal to 0 to 100 microamperes. Least count of microammeter is equal to 2 microamperes. Zero error of microammeter is equal to nil. Observation table for reverse bias voltage VR and reverse current IR. When the reverse bias voltage is 4 volts, the reverse bias current is 2 microamperes. Similarly, the reverse bias voltage is increased and the corresponding reverse current readings are as follows.
Anu,
Using the values of reverse voltage and reverse current, we plot a graph by taking reverse bias voltage along negative x-axis and reverse bias current along negative y-axis. We consider a suitable scale. On x-axis, 1 centimeter is equal to 10 volts. On y-axis, 1 centimeter is equal to 20 microamperes. Origin 0, 0. Now, let us plot the points on the graph. The graph comes out to be as shown here. Let us consider 2 points A 3018 and B 4032 in the graph. In reverse bias, junction resistance is R is equal to delta VR by delta IR. That is equal to 40 minus 30 by 32 minus 18, which is 10 volts divided by 12 microamperes. That is 0.83 into 10 power 6 ohms. Therefore, junction resistance for reverse bias is equal to 0.83 into 10 power 6 ohms. All connections should be neat, clean and tight. Key should be closed only when we are taking the readings. The voltage should be increased in steps of 0 to 1 volt until you observe a significant change in the current. Forward bias voltage beyond breakdown should not be applied.
I am sure that after watching this video, you have now understood how to draw the characteristic curves of a PN junction diode and determine its resistance in forward and reverse bias. Thank you for watching this video.
Hi, hello, good morning everyone. Today we will explain how to plot characteristics of Zener diode in forward and reverse bias, and how to design a simple Zener voltage regulator and to determine line and load regulation. So here is the circuit diagram. So in the circuit diagram we have used a VS variable DC supply and a 560 ohm resistor and a ammeter in series and a Zener diode, and at the output we are using a voltmeter to note down the output voltage. A Zener diode is a unique diode which acts as a normal diode in the forward bias, whereas it has some unique features in the reverse bias. In the reverse bias, when we increase the negative voltage after attaining Vz, that is Zener breakdown voltage, the voltage remains constant but the current increases exponentially. So that circuit we will demonstrate now. So I will be taking a diode, that is Zener diode, and we have taken a 560 ohm resistor, and I have connected a Zener diode in reverse bias. So the black color is cathode and the other one is anode. So we are connecting the Zener diode in reverse bias. So we have connected a diode and a resistor, and between resistor and the diode we have connected a milliammeter. So the positive end of the milliammeter is connected to diode and the negative is connected to the resistor, and we have taken the supply. Supply is given to one end of the resistor, and the negative end of the DC supply is connected to anode of the Zener diode, and we are observing output in the multimeter. So one end of the multimeter is connected to diode, that is Zener diode, and the other end is connected to anode. So this is the circuit of Zener diode. Now I will switch on this one. Now this is my Vs, this is milliampere current, and this is our V0. Now I will vary Vs and will observe what happens to V0 and the current. So as we increase the value of Vs, V0 will also increase. When V0 reaches the breakdown voltage, then current will start increasing exponentially. Now I will slowly vary the Vs. So we can see here V0 is also getting varied, but current is 0 milliamperes. Current is very small till it reaches breakdown. So we are still increasing Vs. Still the current is 0 here. Now we can see current is 0.5 milliamperes. The output voltage is 12.09. I am still increasing the Vs. Now this output voltage remains almost constant, but we can observe the current is increasing exponentially. So for 2.23 it is 3.1 milliamperes. Now I will just increase. So for 2.27 it is 3.6 milliamperes. So if we keep on increasing Vs, V0 will remain constant, whereas the current increases exponentially. So one can clearly observe here. So for small variations of output voltage, the current increases exponentially in the reverse bias. So see here it is still 12.89 or 90. Here it has increased to 15.6. Now if I take the readings, now you can see here so the readings are plotted here. For 1 volt till some 12 volts it is 0.1. Later once it reaches 12 volt, so for a minute change in the output voltage, current increases exponentially. So the reason why it increases after 12 volt means the diode what we have taken is it has cut-in voltage, that is Zener breakdown voltage of 12 volt. So it is 12 VZ Zener diode. So once it reaches 12 volt or 12.1, the current increases exponentially. So we have plotted voltage versus current. Now we will plot the graph V0 versus I once we take the forward bias readings also. Now we will study how to take or how to plot characteristic of Zener diode in forward bias. So in this circuit diagram, now I will replace or I will change the anode to cathode and cathode to anode. I will reverse this diode, then I will get the characteristics in forward bias. Now I am taking the diode, and this diode I am reversing. Now this circuit works in forward bias. Now I will switch on. So in the forward bias, as I mentioned, the Zener diode works as normal diode. So for the normal diode, 0.7 is the cut-in voltage. That means the moment output voltage reaches 0.6 or 0.7 volt, the current will start increasing exponentially. Now observe this output voltage V0 and the current. I am increasing Vs slowly. For 0.18 volts, the current is still 0 milliamperes. For 0.2, 0.3, 0.4, 0.5, it is still 0 milliamperes. Now I am slowly increasing. Again 0.6 volts, current is 0 milliampere. Now we have reached 0.69, current is 0.1 milliamperes. Now 0.70, 0.2. So after 0.7, when I still increase the Vs, so for minute change in the voltage, current is increasing exponentially. So for 0.75 it is 1.3, we can see. For 0.76 it is 2.0, for 0.77 it is 2.8. so for minute change in V0, the current is increasing exponentially. So if I take the readings, so we can observe here. For 0.1 it was 0, 0.2, 0.28, 0.55 up to 0.66, the current is 0 milliamperes. But once it reaches 0.7, so from that point onwards, even for minute change in the voltage, the current is increasing exponentially. So from 0.7 to 0.86, we can see the current is 31.6 milliamperes. So this is forward bias characteristics. Now if you plot forward bias and the reverse bias characteristics, we can see the graph like this. So in the reverse bias, once it reaches Vz, that is breakdown voltage remains constant, whereas current is increasing exponentially in the negative direction. Whereas in the forward bias, when voltage reaches 0.7, so the current will increase exponentially. So we have to plot graph I versus V in both forward bias and reverse bias. Now consider the same circuit. Now we will go for the second part, that is to design a simple voltage regulator to determine line and load regulation. First we will find out line regulation. So we will connect the circuit. We have already connected this one. Now since it is in forward bias, now I will go back to the reverse bias. Now the meaning of line regulation is, I will vary Vs, supply voltage, and I will measure the output voltage V0. So as we have already seen in the reverse bias characteristics, as we keep on increasing the value of Vs, V0 will also vary, but after a certain point, when it reaches reverse breakdown, the output voltage remains constant. So now I don't need that is current value, so I will switch off the milliammeter. Now observe carefully Vs and V0. So I am increasing the value of Vs, correspondingly V0 is also increasing. So for 2.8, 3.6, 3.9 we are increasing the Vs, V0 is also increasing. We can clearly see here. Now the moment it reaches 12.1 or 12.2 volts, then the output voltage remains constant. So now still I am increasing this one. We have reached 14 volt, 15 volt, but output is there in 12.2 only. So now we have reached 15 volt, 16, 18, 20, but it remains in 12.5 only. That means once it reaches reverse breakdown, output voltage remains constant even though we vary input voltage Vs. So now we have reached even 23 volt, 24 volts, but we can clearly see the output voltage remains almost constant. So the meaning of the line regulation here is, even though I vary Vs, my V0 should remain constant. So this one we can clearly observe in the readings. So we have noted down Vs versus V0. So initially for increase in Vs, V0 was also proportionally increased. So as we keep on increasing, so once it reached 12.4 volts or 12.7 volt, the output remains constant. So Vs is continuously varied, whereas output remains constant. So this is what line regulation is all about. So even though I vary Vs, V0 should remain constant. This is line regulation. Now we will move for the last one, that is load regulation. For the same circuit which you have studied till now we have connected one decayed resistance box, a variable resistor across the Zener diode, and now we will be proving, even though we vary load resistance RL, the output voltage remains constant in Zener diode. So now I am taking a decayed resistance box DRB. I am connecting in parallel to the Zener diode, which you have already connected. We have connected decayed resistance box in parallel. Now one thing we have to remember here, we are varying RL and we are noting V0. So this Vs we should keep constant. Since I am using 12 volt Zener diode, I have to set Vs some 1 or 2 voltage higher